Hello and welcome to our physical sciences session. My name is Temba Ncube. Today we are focusing our attention on a certain aspect of matter and materials which has to do with exploring exactly what happens when a form of matter changes from one state to another. So the word state and phase, we shall for now use them interchangeably to refer to one and the same thing. Without any waste of time, let's look at the bigger concept map in as far as how exactly change or phase of matter fits into the broader matter and materials knowledge area, right? Okay, so we are saying that now we understand that it has a lot to do with a physical change, which has to do with also the properties of matter. But we also want to explore exactly what exactly happens when a phase changes from one form to another in a given type of material or matter. Okay, so the thinking exercise that's going to guide our discussion for today is, have you ever thought about, number one, what exactly happens to a substance when a phase change occurs? So our emphasis in this case is exactly on the change of phase from one to the other amongst the three phases that we know of, which is the solid, the liquid, as well as the gas. And then the second thought that we want to entertain in our discussion is that what is the role of energy, when a change of phase of a substance occurs? So these are the two big ideas that we want to try and use to guide our exploration of understanding exactly what happens when there's a change of phase of matter. Right, now when it comes to the terminology, which is the definitions, which is an all or nothing kind of an arrangement. Now remember, we need to refer to the guidelines in terms of the examination so that we get the accurate or what exactly the examiner needs, because different sources will obviously phrase the same definition maybe in a different way. But beyond that, understanding the key words that must be used in the correct context is also very important. We cannot overemphasize the importance of that. Right, so what are some of the keywords for today? We talk about the freezing point, which has to do with the temperature at which a certain phase change occurs. But let's be careful not to confuse between the process, okay? So freezing becomes the process, and then the temperature at which that process occurs or that phase change occurs, it's obviously the freezing point. So these are actually the different temperatures at which phase change occurs. So this has to do with temperatures, okay? It has to do with temperatures at which phase changes occur. So these are various phases that we're talking about. It could be from liquid to gas, or solid to gas. So these are temperatures at which phases change, okay, for a particular substance. So the processes that has to do with the melting point is obviously the melting, okay? Boiling point has to do with the boiling or change of phase from liquid to gas, as well as condensation. So these are the key terms that you need to pay careful attention to, right? Okay, now what is it that we know already? We know that matter exists in any of the three states, okay? So whatever substance that you pick up or you identify, it can, depending on the condition of temperature, pressure, they would either exist in the form of a solid, a liquid, or a gas. So it entirely depends. But over and above, we are all saying that now. These are the three phases that are important that we need to take note of. So these are obviously the solid, the liquid, and the gas. Okay, now we'll take turn to look at one of them at a time and try to look at the properties of each one of them so that we understand exactly what happens during the transition in terms of the state or the phase. Okay, now let's look at the properties of a solid very quickly. Okay, let's use the simulation just to guide our discussion. Right, here is a simulation that shows the behavior of particles that make up, in this case we've chosen water as an example. what are some of the important things that we can immediately pick up from the simulation is that these particles, are they in a state of motion? Maybe that's the first question that we need to ask ourselves. Yes, indeed, they are in motion. But to what extent do these particles move? They are only vibrating within the fixed position, okay? Now, also, you would also realize that when you carefully analyze that simulation, it shows that much as the particles are vibrating or shaking, they maintain a certain definite shape or volume in terms of space. This is in the backdrop of the fact that we understand that any form of matter has got mass and occupies volume or a space, or it's got volume. So there is a definiteness of shape as well as volume in as far as the solid is concerned. Okay, now the movement of the particles suggests that there are some forces that act between the particles. These forces are relatively stronger. So the term relative suggests that it's by comparison to another phase of matter. Okay, let's go back to our simulation, our presentation, and look at the individual properties or characteristics of a solid. So the vibration suggests that there is some sort of movement, okay, that the particles are experiencing. And the moment we spoke of movement, we're thinking immediately of the kinetic energy. Do these particles possess kinetic energy? Most definitely. So within fixed position, it means they maintain their position. However, the movement is restricted. Why? Because the forces are very strong. So the word very suggests that in comparison to other forms of matter, these are actually stronger, okay? And then thirdly, we are saying that these particles are closely pegged, okay? Why are these particles closely pegged? Because we attribute that to the strength of the forces that exist between the particles. I think it all comes together in that way. And also, they are generally incompressible. What does it mean when we say solids are incompressible? If you analyze the arrangement of particles that actually make a solid, there are very little spaces in between them because of these strong forces, because they are closely pegged. So it becomes difficult for us to be able to compress a solid so that it changes its shape, or it changes, its size, whichever way you choose to look at it. But because of these smaller forces, which can be attributed to the stronger forces, all solids are incompressible in general. Okay, so they retain their shape, then we would say they've got a definite shape, right? So all solids have got a definite shape. Okay, it can be regular or irregular. By regular, we mean it could be a block, it could be a prism. These are regular shapes. It can be also irregular, right? Okay. Now, the other property of a solid is that they have specific melting point under standard condition. So we are saying that a given solid material or substance will melt at a certain temperature under different conditions. Okay, that's the long and short of it. Okay, now let's look at the properties of a liquid. Okay, what is it that we know about liquids? But before we do that, let's draw our attention to the simulation and try to look at, for argument's sake, a liquid. Water as an example. You may obviously pick up some of the obvious, properties that, yes, indeed, the particles are in a state of motion. There is some movement, but the movement is much greater compared to those between, the solid particles. And also, there is some evidence that suggests that the forces are comparatively weaker than those of a solid. In terms of shape, you'd realize that there is no definite shape. In this case, the liquid takes, the shape of the container. So these are some of the obvious characteristics or properties of a liquid that must come to mind, right? If you can go back to our simulation to actually look at the slides in terms of the summary, it says here that the particles, they slide past each other, okay? So sliding suggests that there is some movement that the particles are experiencing, but these forces, by comparison, they're actually weaker than those of a solid, right? And also, the forces between the particles are weaker, so that's the comparative term, okay, compared to those in a solid. The spaces exist between these particles. There are some spaces, but these spaces are actually smaller. Pay careful attention to that, okay? they are generally incompressible and they exert pressure in all directions. So what we would know even from, you know, our you know, obvious knowledge to say that, okay, if you have a liquid, it's very difficult for you to compress the liquid so that it occupies a lesser space. Why? Because the spaces that exist between the particles of any liquid substances are so small such that, you know, the difference in terms of compressing it changing its volume is quite insignificant. So it is too small to notice. As a result, we can safely say that generally most liquids are actually incompressible, right? Okay, and then we also understand that they do not have a definite shape. That's why they take the shape of the container, okay? And they have a specific boiling point and freezing point under specific conditions. So the boiling point has a lot to do with the temperature at which a certain phase change occurs, as well as the freezing point, okay? But this is under standard conditions. We shall discuss what exactly standard conditions are all about, okay? Right, what about gases? Let's use the same simulation, but now draw our attention to a gas, right? Here is a simulation that resembles the behavior of particles of a gas. It's still the same substances, which substance that we're using, water molecules. Now you can immediately tell that the extent of movement of particles is by comparison far greater than those of a liquid as well as a solid, okay? And also the spaces. Can that be a suggestion about something which has to do with the forces that exist between the gas particles? Definitely. So there is a lot of spaces due to weaker forces, and that's why these particles are actually free to move, you know, in a random or haphazard fashion. As a result, a gas tends to fill up any space that's available within the shortest period of time. Why? Because these particles are actually moving very, very fast. Okay, so in short, what are we saying in as far as the gases are concerned? We know that the particles, the movement is random, but this movement has a lot to do with the kinetic energy. All right, we shall talk to kinetic energy a lot, which has to do with the movement of particles, you know, due to their speed. The faster they move, the greater the kinetic energy or the extent of movement. We also realize that the forces are very weak. So very is the comparative term. These forces are weaker compared to liquids as well as solids. There are huge spaces between the particles because of weaker forces, right? And also, these are actually compressible, okay? Now, we are saying that because of spaces that exist between, you know, gas particles, it's easy to compress a gas, you know, so it can occupy a lesser volume. So that is possible, which the same cannot be said about solids as well as liquids, right? Okay, now, and all gases exert pressure in all directions. We shall talk about what exactly a pressure of a gas means, you know, because you immediately realize that, okay, so if we were to model the behavior of particles of a gas, this random movement of particles, you know, filling up, you know, all the spaces available has a lot to do with the pressure that, you know, a gas exerts inside, you know, in a container. So the faster these particles move, the greater the pressure, and it has a lot to do with the energy of movement of these particles. But remember, all this is possible because there are weaker forces that exist between the particles of a gas. As a result, there is a greater extent of movement, and there are a lot of spaces in between these particles, right? And also, we can safely say that they have a specific condensation point under standard condition. Okay, the word condensation is one of the key terms that we referred to earlier on. So condensation it has a lot to do with the phase change from, you know, gas to liquid. So when a gas condenses, it liquefies, it becomes a liquid. Okay, that is a phase change, which is the big idea of today's discussion. But remember, for condensation to occur, there needs to be some cooling of some sort, which takes us to the second question of our discussion to say, what is the role of energy in as far as, phase change is concerned? Okay, so this is the most important part of our our introduction in as far as the phase change and us understanding what exactly happens when there's a change, in a state of matter, and how exactly energy, impacts on the phase change. That said, let's take a short break. We'll join again in the second segment where we take the discussion further. Let's take a short break for now. Welcome back to our second segment. We're still looking at the exploration of what exactly happens, to matter when there is a phase change that takes place. Now, we want to focus our attention on what exactly happens in terms of, the energy. We'll also try and incorporate some of the key terms that we discussed in the first segment. Now, without any waste of time, let's look at the detail behind, freezing as a phase change. Now, the key term that relates to that change of that state of matter is freezing point. Okay, what is freezing point? By definition, freezing point is the temperature. So it is actually the temperature. Okay, so freezing point is actually the temperature at which a liquid completely changes to a solid. So the change, the process involved is when a liquid changes to a solid. Okay, that's what this is, the process involved in terms of freezing. Okay, and then when a substance freezes, there is a change of phase. Okay, the change of phase is from liquid to solid, and now it's still the same substance. However, the state in which it exists is what has changed. So this is more of a physical change. Okay, so a physical change involves, a change of state of matter. However, the chemical properties of that material remains the same. The only thing that happens is that the substance changes from a liquid to a solid. Right, and then the freezing point of a substance will depend on how strong the forces, that exist between the particles of that substance. So as freezing occurs, it means that, remember, in terms of properties, the particles in a liquid, they're actually sliding past each other because the forces are comparatively weaker. So when freezing takes place, it means the packaging of particles also changes. Okay, it means the forces become stronger, which is why the substance becomes more compact, and then it assumes a certain shape for that matter. Okay, right. That's what it means in as far as freezing is concerned. Now let's focus our attention on melting point. Okay, so melting point is actually the temperature. I'll highlight the term temperature because it's actually, more of, what happens in as far as, the energy is concerned. So the temperature at which a solid completely changes to a liquid is the melting point. So the phase change involved here is, from solid to liquid. Okay, so it's from solid, changing to a liquid, which is actually the opposite of what happens when a substance melts. So this is also, again, a physical change. Why are we saying this is a physical change? Because the physical properties of the material will change, but it will still be the same material in terms of what makes up that material. Same particles, the only thing that's going to change here is the packaging. So when a substance actually melts, it means the forces become weaker, and the energy involved with that is that you have to, you heat a substance, and then once you heat at a particular temperature, the solid will turn into a liquid. So that's the phase change that is involved in as far as melting. So at the melting point of a substance, the solid and the liquid phase are in equilibrium. Now, what this means is that we have a solid coexisting with a liquid. So this change actually is in the direction from solid to liquid. So when we talk about equilibrium, we talk about a state of balance. For now, let's think of it in terms of the state of balance between the two phases, okay? Now, the melting point of a substance is also influenced by the strength of the forces that exist between particles. What does that mean? For us to say substance X has got a certain, melting point, what that simply means is that temperature is actually influenced by how strong the force is. So if a substance is got a higher melting point, what does it mean? It means we have to supply more energy. It means the change of the phase will happen at a comparatively higher temperature than for a substance that has got, a weaker forces between the particles, okay? So that's a very important thing to say, because when we will do a problem in the next segment, we'll talk about the relationship that exists between the strength of forces between the particles and the melting point, or the boiling point for that matter, which takes us to, the next slide, okay? So the temperature at which a substance, which a liquid substance in a liquid phase changes to a solid, that's the freezing point, we know that. Now, freezing is the reverse phase change of melting. So we've got solid, okay, to liquid, right? That's melting. So if we move in that direction, we heat. Then if we move from liquid to solid, we cool, okay? So cooling will, consequently result in a decrease in temperature. So if solid to liquid, that's the melting. So melting is actually the process. Now, at the melting point, this process or this change from solid to liquid would actually take place. And then from liquid to solid, that's the freezing. So freezing becomes the process involved when a liquid substance completely changes into a solid, okay? So this is the big idea in as far as the transition of state of matter between solid and liquid. We need to understand it in this context, okay? So freezing occurs when a substance is cooled. Now, this is the opposite of heating, okay? But melting will actually occur when a substance is heated. We don't talk of a, to say we increase the temperature. When you heat, the temperature will automatically increase. So the language, again, there is very, very important, okay? Now, let's talk about boiling point, okay? What is boiling point? Boiling point of a substance. So we want to qualify that. Is boiling point of a substance, because in the context, we must refer to a specific substance. So I've used substance X as an example, and it can be anything. So boiling point of a substance is actually the temperature, yet again, okay, at which vapor pressure of a substance is equal to the atmospheric pressure, okay? Now, boiling involves the transition or the change from liquid to gas, okay? Now, if we heat a liquid, what happens? It turns into a gas, or it vaporizes. Now, if it boils or evaporates, it simply means that now the forces between these particles of that substance, they become actually weaker. And then the opposite of that is actually condensation, which is one of the key terms that we spoke to. So if a gas or a substance condenses, it means we cool a gas, and then while we do that, the forces become weaker, the packaging or the physical properties of that material or that substance changes, and then that substance changes to a liquid from a gas. So the reverse process of boiling is actually condensation. So this is something that we maybe already know, but let's try and link the two in terms of how those two phases of matter relate to each other and the processes involved. Now we are able to distinguish between boiling point, okay, as in the temperature at which the vapor pressure equals that of the atmospheric pressure, as well as the process in itself which is involved, which is actually the boiling, right? Okay. Okay, now evaporation of a substance may occur at a temperature that is comparatively lower than its boiling point. Now, the key idea here is to say that the process of evaporation as well as the boiling point. This is a possibility. It does not follow that evaporation of a substance occurs at a boiling point. It can be lower. Why? Because this is entirely dependent, again, on the conditions under which it takes place. If you think of the boiling point of water, ordinarily would say it's 100 degrees Celsius, but it can actually be less than that, say 97. So it depends, again, in terms of the atmospheric pressure. So the process or the conditions under which the process takes place will influence the boiling point or the temperature at which that process actually occurs. Very, very important point, right? Okay. Now, the state in which a given substance exists depend on its melting point and boiling point, okay? Below is a list of substances and their respective boiling points and melting points. Now we want to determine the state. Remember, state, either solid, okay, liquid, or gas, right? So we are given three substances, okay, at room temperature, which is 23 degrees Celsius. Okay. Now, we can think of this as our standard condition. We're saying that these substances, we are given these substances at a temperature of 23 degrees Celsius. Now, okay. Now we have got iodine, bromine, and chlorine. The melting point of iodine is 113 degrees Celsius. Okay, at an atmospheric pressure of 1 atmosphere. The very same substance boils at 184 degrees Celsius at 1 atmosphere. Okay, so now we know the difference between melting and boiling point. Okay, now having said that, we want to decide whether for each of these substances at that temperature of 23 degrees Celsius, does it exist as a liquid, a solid, or a gas? Right. Now at 23 degrees Celsius, okay, we have got iodine, which melts at 113, okay? So 23 degrees Celsius is actually lower than 113, okay? Now, it means then for iodine, at that temperature, it will still be in liquid form, okay? Right, but then again, if you check, 184 degrees is actually the boiling point, okay? For iodine to turn into a gas, we must reach a temperature of 184, okay? Right, and then for it to melt, we need a temperature of 113. Now let's look at bromine. Bromine melts at -8, all right? It melts at -8 and boils at 59. Now we have to compare these two temperatures to the 23 degrees Celsius, okay? So if bromine melts at -8, okay, and 23 is greater than -8, then it means bromine will be a liquid, okay? While at 23 degrees Celsius, iodine will still be in solid form, okay? It's very important to note that. Then chlorine boils at -34 degrees and it melts at -102. So 23 degrees is actually greater than -102, okay? And also, it's also 23 greater than that. It means than -34. It means then chlorine will exist as a gas at 23 degrees Celsius, okay? Now, the long and short of this is that the state of matter is entirely dependent on the temperature at which that substance is given, and we also have to compare that to its melting and boiling point. So if a substance is the temperature at which that substance is given is actually less than the melting point, then it will be a solid, okay? Now, if for example, the melting point and the boiling point of that substance is given, okay, and then the temperature which is given is actually, the melting point is less than the temperature that's given and less than the boiling point, that substance will actually be a liquid, okay? Now, we can use, this is 23 degrees Celsius, okay, is less than, if we can go back to the iodine, okay, is less than 113, okay? So if it's less than 113, it means this substance will be a solid, okay? 113 degrees Celsius. So it means this substance will be a solid. But then if you take 23 degrees Celsius, okay, which is the temperature at which, let's say for argument's sake, bromine is given. If you go back, you'll see that bromine melts at -8, okay? -8 is less than 23, but at the same time, 23 is less than 59. So if the temperature, that's given, which is 23 degrees, is between the melting point and the boiling point, that substance will be a liquid, right? The substance will be a liquid. And then if the temperature is given of that substance is actually greater than the boiling point, then that substance will be a gas. This is what actually happened with chlorine in the previous example that we just spoke of, right? Okay. So these are some of the, the ideas to say, how do these, temperatures at which a phase change influence the state in which the substance actually exists. That's very, very important. So in the next segment, we'll try and look at exactly what happens in terms of, the energy, and we'll look at the heating curve of a substance, which is a very, very important part, which links with what we've just discussed in terms of how energy plays a role in as far as phase change of a substance is concerned. Let's take a short break for now. Welcome back to our third and final segment. We're still exploring, at a microscopic level as to what exactly happens when phase change of a material takes place. For now, we'll shift our attention and look into, a practical investigation to, try and keep track of data in terms of temperature, and time. This would involve the heating of water. As an example, okay? So apparatus, these are actually the equipment that we use, in the lab at our schools to try and understand, okay, if we want to maybe verify a non-scientific fact, we would conduct an experiment. So this would obviously deal with also some aspects of how do we present the data that we've extracted from an experiment. So the piece of apparatus that we need to be familiar with, it's a beaker, okay, which is in most cases is a glass container. We'll also use ice. So ice in this case will be in solid form, okay? Take note of that because we'll be heating and we want to try and, understand, as to what exactly happens when a substance changes from solid to liquid and then to gas. And then a thermometer then is an instrument, all right, that we use to actually measure temperature, okay? And then we'll also have a tripod stand on which we'll place the beaker for us to be able to heat water, and then the gauze becomes the platform on which the beaker is placed, and then the burner becomes our source of heat energy, right? Okay, now suppose these are the results that we obtained. So below here in this case we've got a graph of temperature of water over time while we heat this substance, okay? Now you'd realize that within the first 3 minutes, there is no temperature change, okay, as we heat that substance, okay? And during the first 3 minutes, while we're heating it, the temperature is remaining constant. And this is coupled by a change of phase from solid to liquid. So when we talk about the interval of 3 minutes, we're talking about actually this, which is actually 3 minutes there, okay? Because our time axis is on the horizontal axis, and then it means this time is actually our independent variable, okay? Something also that's important when as far as the investigation is concerned. So we can decide, to say, okay, we'll take the temperature reading within every 3 minutes or every minute in time interval. So that's for us to decide. We can change that, we can manipulate that. Hence we are saying time becomes our independent variable. And then as a result of recording time within fixed time intervals, then we would also try to check how the temperature changes. Remember, we want to keep track of how temperature changes when a substance is heated from solid until it is a gas, right? Okay, and then between the 3rd minute and the 8th minute. Now, so one may ask, how long did it take for the substance to change from liquid to gas? So this was the phase change that was involved when the substance actually was boiling. So this is actually the boiling point, okay? So this is boiling as in the process. So the time that it took between the 8th and the, more or less the 11th minute, the substance was undergoing a phase change. And then this happened at a temperature of 100 degrees Celsius. So what that simply means, boiling is the process which took place at that temperature. So we need to be mindful of that, okay? And then the questions that we are asking ourselves, what exactly happens during phase change of a substance? Remember, phase change is involved, of a substance changing from either solid to liquid or liquid to gas or vice versa. Okay, but because this is heating, so we are saying that from solid, we went to liquid, okay, because we were heating, and then we obtained a gas. So those are the 3 phases of matter, and we want to try and understand what happens in each of those phase changing. Okay, the following aspects actually remain constant or do not change. The size of the particles stays the same, okay? Also, the shape of the particles that make up that substance stay the same. The total mass of the substance also does not change. So if, for argument's sake, we go to our simulation and look at, let's for argument's sake start with a solid. And then if we hit the solid, what happens? The extent of movement of the particles gets greater and greater, okay? Now you also see that the spacing between the particles as we hit this substance becomes more and more, okay? Now, this is what is exactly involved in as far as phase change occurs. But you also want to take note of what exactly happens in terms of temperature, okay? Just take note of that. As we heat the substance, the temperature is increasing, which is exactly the trend that we obtained from the results that we showed on the graph, okay? Right, so if we can quickly go back to that. So we are saying the particle sizes stays the same, the shape of particles does not change, and also the mass. So the amount of matter remains the same. Why? Because this is actually a physical change, okay? This is actually a physical change. So within a physical change, none of these quantities changes. That is size, shape, as well as mass, right? Okay. Now the speed of particles remains the same, okay? The speed, remember, is how fast these particles are moving. So when a phase change occurs, either from a solid to a liquid, the speed of the particles remains the same, okay? And now the speed actually is an indication of the temperature of a substance. So if the speed remains the same, it means also temperature will not change during a phase change. So when a substance is heated, a solid, so when we heated the ice, okay, and then it changed into a liquid, okay, you'd realize that the temperature remained constant. So if I can quickly go back to the table of results, actually the graph, you see within the first 3 minutes, okay, within the first 3 minutes, what is actually happening? Temperature remains the same. That was the melting that was taking place. So the process of melting took place, okay? And you see that this occurred at a temperature of 0 degrees. So the temperature of 0 degrees of this substance of water, which is water, did not change in the first 3 minutes, right? Okay, and we are also saying the forces between the particles become weaker, okay? Now, as we heat the substance, these substances these particles, they actually gain more energy, okay? While they gain more energy, it becomes easier for them to overcome the forces that keep these particles together. This is accompanied by a change of phase, either from solid to liquid or liquid to gas, okay? Right, and then the spaces, we saw that the spaces which affected the shape of the particles, as we heated, the spaces got bigger and bigger, right? Okay, now we have a different scenario now, for argument's sake, to say, okay, we have a graph below that represents the heating curve of a substance X, okay? It could be any substance, but you'd realize that the trend is actually the same. So at a temperature of negative 15 degrees Celsius, that substance is actually a solid. So when we heated it for the first 4 minutes, what is happening? The particles gained more energy, and then the phase change occurred at interval 2. So at interval 1, the substance is still a solid, okay? But at 5 degrees Celsius, there was a phase change. Why? Because at that, between the 4th and the 8th minute, what actually happened? The temperature remained constant, okay? Then this substance was heated, particles gained more energy, which explains the temperature increase within stage 3 of that curve. And then at stage 4, another process took place and there was a phase change. And then here, it was actually the boiling, okay? Now, after phase 4, these particles are actually in gaseous form. So the further heating will sharply increase the temperature of these particles because they're now moving faster and faster. Now, in other words, I think we get to a point where we really appreciate that there is a direct link between temperature of substance and how fast the particles of that substance move. Okay, when we heat, particles gain energy, they move faster and faster, meaning that at a higher temperature, actually we'll have these particles having a high speed or moving very, very fast. Okay, right. And then from this graph, we would ask ourselves simple questions. In which part of the graph does the substance have a definite shape? So this takes us back to the properties of materials, okay, or of a solid. So definite shape has to do with characteristics of the state of matter. So we ask ourselves when, at which point on that graph actually is the substance in solid form. So if we can go back, we understand that between 0 and 4 minutes, we actually have the substance in solid form. So that is actually stage 1 of that graph. So on stage 1, we understand that this substance is actually a solid because we have to relate this property to a particular state of matter, which is actually the solid, okay? And then B says, what is the melting point? So melting point, we go back to the terminology. We ask ourselves, at a melting point, what exactly happens to a substance? The substance changes its state or its phase, okay? So the process involved at the melting point is, a substance changing from a solid to a liquid, and that happens at a constant temperature. So if we go back to the graph, you'd understand that between the 4th and the 8th minute, that's when there was a phase change, and this happened at a temperature of 5 degrees Celsius. So 5 degrees Celsius is actually the melting point. But the question says that, what is the melting point? So we simply go and take it off or read it off from the graph. The temperature at which that phase change took place is actually 5 degrees Celsius, okay? C says, which part of the curve are the particles of substance X furthest apart? This again takes us back to the properties of the 3 states of matter. We know that when particles are furthest apart, they are loosely pegged, meaning the forces that exist between the particles are actually weak. So this will be a gaseous state. So in this case, we're asking ourselves, when was substance X a gas? So if we go back to our graph, we would understand that at stage 5, it's already a gas, and now we are heating gas particles. They are moving even faster. But do not confuse that to stage 4, because stage 4 involved the transition or the change from liquid to gas. So at stage 5, we appreciate that this substance was actually a gas. Okay? So D, which part of the curve are the particles of the substance moving at high speed? Okay, higher speed suggests that the forces are actually weaker, okay? The spaces are bigger, meaning that the substance is still a gas. So we're still asking the same thing about the properties of a gas, okay? Right. Now, and then if we are to quickly interpret the graph, in short, we are saying at stage one, the substance X is a solid, and when you heat it, they gain energy. That's why they move faster and faster, which accounts for a temperature increase, okay? Stage two involves which physical process? The melting. Now, the solid substance begins to melt, so the speed of the particles remains the same, so does the temperature during phase change. Now, at stage three, we've got a liquid which absorbs more energy, and the temperature increases sharply. Stage four, there is a phase change, that's why the temperature remains the same, okay? Right, and then stage five, the substance is already in a gaseous state. Now, you continue heating these gas particles, so these vapor particles, they continue again to absorb even more energy, and the temperature rises. That's why there was a sharp increase of temperature within a short space of time under stage five. So if you heat a gas more and more, it gains even greater amount of energy, right? So this is the big idea in as far as, you know, the energy and, you know, how a particular substance actually changes phase. So in terms of the, you know, phase change, we understand that heating increases the temperature. Obviously, the cooling will also have an opposite effect. So in this scenario, we only looked at the heating part, but there is the other side to it again, which has to do with the cooling. Even the trend may not necessarily be the same, but it's just that it will be a downward trend in terms of, you know, because you, instead of heating, you actually cooling. So for today, that's all that we had to do in terms of exploring phase change and understanding how energy plays a role in as far as the physical change between the three states of matter actually takes place. With that said, from myself, Themba Ncube, it's cheers and bye-bye for now.